Assalamualaikum and hello everyone. My name is Farhana Natasha Fazil, and in this video I will talk about the summary of the general article about strain rate effect on the tensile behavior of textile-reinforced concrete under static and dynamic loading. First of all, we look at the objective of the study. The objective is to investigate the strain, deformation and fracture behavior of textile-reinforced concrete TRC subjected both to low and high rate tensile loading ranging from 0.0001 to 50x. Next, I will give a brief introduction of this article. Textile-reinforced concrete is a relatively new class in the array of cement composite system which exhibits strain hardening behavior with enhanced strength and ductility. This material is strong enough to be used for production of load-bearing structural members in application such as structural panels, impact and blast-resistant structure, repair and retrofit, earthquake remediation, strengthening of unreinforced masonry walls, and beam column connections. Next, mechanical properties of cement-based materials are well known to be dependent on the strain rate. Most of the experimental studies under high strain rate have been performed using split Hopkinson bar SHB test in cylindrical specimen or a modified SHB apparatus with state-of-the-art instrumentation. Next, dynamic tensile data on fiber-reinforced concrete is very limited. The dynamic behavior of strain hardening cement-based composite reinforced with PVA fiber under tensile load. It was shown that for tensile tests performed at strain rate up to 10 to 2s with increasing strain rate SHCC exhibited an increase in tensile strength and a decrease in strain capacity. High strain rate were tested using a high rate servo-hydraulic testing machine. The effect of the addition of short fiber on the static and dynamic response of TRC was investigated, and the microstructure of both composite and fiber was observed after the test using NESEM. An increase in tensile strength, strain capacity, and work to fracture was observed for strain rate up to 0.1s with increasing strain rate. There are a few methods used in this study. Firstly, material and processing. Second, low-speed tensile testing. And lastly, high-speed tensile testing. Firstly, we look at material and processing. A finely grained matrix was used in mixing the textile-reinforced concrete, which consists of cement, fly ash, microsilica and quartz sand. This table summarizes the matrix composition. Superplasticizer with a basis of naphthalene sulfonate was added in order to achieve sufficient flowability. Textile-reinforced concrete was produced with and without the addition of short glass fibers to the matrix. Polymer coat by fabric made of alkali-resistant glass was used as reinforcement. This figure shows biaxial textile reinforcement made of AR glass. This photograph showing that the spacing between the yarns is uniform in the warp direction, but not uniform in the weft direction. Next, the degree of reinforcement was calculated for one layer of fabric in volume as 66.33 mm²/m. In total, 3 layers of fabric were applied. The fineness of the weft and warp threads as well as the mean spacing between the yarns is as shown in this table. The thickness of the plate was 10 mm. The plates were demolded at the age of 2 days and stored in water until the age of 7 days. Next, the second method is low-speed tensile testing. Low-speed tensile testing was performed using an installed universal servo-hydraulic machine under a cross-head displacement control regime. The force was transferred to the plates via fixed steel plates glued to the TRC specimen as shown in this figure. The strain was measured by means of 2 LVDT fixed to the specimen and oriented in the direction of loading. Next, we proceed with the next method, which is high-speed tensile testing. Dynamic tensile testing was performed in high-rate servo-hydraulic MTS. The setup is as shown in this figure. Once the test starts, the actuator accelerates to reach the specified speed and then maintains that velocity. During this range of motion, the slack adapter engages and transfers the force to the specimen. The slack adapter consists of a sliding bar with a cone-shaped end that travels within a hollow tube. It travels freely with the actuator at the specified velocity before making contact with the cone-shaped surface of the sliding bar. This eliminates the initial effect of the lower grip and actuator during the acceleration stage. Next, we proceed with the result, discussion and analysis of this study. This figure shows representative stress-strain curve obtained from the tensile test performed at strain rate ranging from 0.0001s to 0.1s of TRC with plain metric and for TRC with the metric reinforced by short glass fiber. From a macroscopic perspective, the bend over point BOP of each of the curve correspond to the formation of a first metric crack crossing the entire cross-section. 5 distinct zones are identified using Roman numeral, with 2 zones prior and 3 zones after the bend over point BOP. Zone 1 corresponds to the elastic linear range where both matrix and fiber behave linearly. The strain range within Zone 2 is associated with formation of matrix microcracks, however, no single crack was traversed the entire width. Next, Zone 3 is the post-BOP stage is characterized by formation of distributed cracking. And next, Zone 4 comes after completion of the cracking phase. This zone is dominated by progressive damage and is characterized by a crack widening phase, ultimately leading to failure. In Zone 2 and 3 of the stress-strain curve, the type of short fiber used mitigated cracking and bridged the small cracks, thus enabling a thinner crack pattern and smaller crack width when compared to TRC without short fiber. The short fiber bridging mechanism can lead to a non-uniform widening of the formed macrocracks, which has still to be shown by precise measurement of crack opening history. This figure shows typical stress-strain curve obtained at high strain rate on TRC specimen with and without short fiber. The shapes of the curve differ significantly to those obtained for lower strain rate. However, there was a similar multiple cracking pattern in combination with strain hardening behavior. Lastly, the gauge length effect was investigated by testing specimen with gauge length ranging from 50 to 150 mm. This figure depicts the effect of gauge length on tensile strength and strain capacity of TRC. The number of cracks increased considerably with increasing the gauge length. The greater number of cracks observed for the specimen with larger gauge length increased the probability of failure localization, leading to a reduction in the strain capacity. This behavior suggests that proper attention should be given to the gauge length when deriving constitutive equation from direct tensile test result performed in TRC. This table has summarized the result obtained. Lastly, the conclusion of this study is for tensile tests performed up to 0.1s, an increase in tensile strength, strain capacity, work to fracture, and first crack strength both for TRC with plain matrix and TRC with short fiber was observed. The addition of short fiber increased first crack and tensile strength for strain rate up to 0.1s. When tested at the rate ranging from 5s to 50s, the TRC continued to tend to increasing tensile strength and work to fracture, but to a decrease in the strain capacity. This lower strain capacity was traced back to the increase in the stiffness of the composite in the post-crack region during the tensile test. A drop in tensile strength was observed when shifting from low to high strain rate. This drop was attributed to possible strain rate effect on the glass fiber and stress concentration in region close to the lower grips during high-speed tensile tests. And last but not least, the study of the gauge length effect showed a decrease in both tensile strength and strain capacity when increasing the free specimen length. That's all from me. Thank you. Till we meet again. Bye-bye.